On June 8, 2004, neurologist Dr. Maria Petersen received a call from Tórshavn Hospital that would uncover one of Europe's most extraordinary genetic mysteries. A 12-year-old boy had been brought in with severe muscle weakness, difficulty breathing, and progressive paralysis, symptoms that pointed to a condition so rare it affected only 1 in 100,000 people worldwide. But this was the 4th case of phosphofructokinase deficiency she'd seen that month, all from the same small village of 300 people on the remote Faroe Islands. What Dr. Petersen discovered wasn't just a medical coincidence. It was evidence that 100 years of Viking isolation had created a genetic time capsule in the North Atlantic. The 50,000 descendants of Norse settlers hadn't just preserved their ancient culture. They had accidentally preserved Viking-era genes, concentrating rare genetic conditions at rates that stunned the international medical community. Before we dive into this incredible story, let us know in the comments where you're watching from, and whether your community has any unique genetic or cultural heritage that connects you to your ancestors. Stay with me until the end, because what happened on these windswept islands reveals how geographic isolation can become genetic destiny, and why the Faroes' genetic legacy became crucial to understanding human disease across the globe. The Faroe Islands exist where most maps end. 18 volcanic islands, scattered across 540 square miles of the North Atlantic, positioned precisely between Iceland and Norway, more than 200 miles from the nearest landmass. These windswept outcrops of basalt and grass rise dramatically from waters so turbulent that medieval sailors called them the islands at the edge of the world. Today, approximately 50,000 people inhabit these islands, concentrated in small coastal villages that cling to fjords and harbors. The landscape is severe, vertical cliffs plunging 1,000 feet into crashing waves, mountains perpetually shrouded in mist, and weather so harsh that communities can be isolated for months at a time during winter storms. This isolation wasn't always a challenge. In 825 AD, Norse Vikings first discovered these uninhabited islands during their westward expansion across the Atlantic. According to the Viking-era saga, a Norwegian chieftain named Grimur Kamban led the first settlers, fewer than 100 individuals who brought their families, livestock, and Norse culture to establish permanent settlements. By 1000 AD, the islands converted to Christianity, which paradoxically increased their cultural isolation. The Faroes developed their own language, traditions, and social structures, distinct from both Norway and Denmark. When Danish rule was established in 1380, the islands fell under Copenhagen's control, but the remoteness meant that Danish influence remained minimal. The Faroes continued their traditional maritime economy, fishing, whaling, and sheep farming, with limited contact with the outside world. By 1948, when the Faroe Islands finally achieved home rule from Denmark, their population had grown slowly over centuries from that original founding group. But the genetic isolation established more than a millennium earlier had already created something unprecedented in modern Europe. A population that carried the genetic signature of their Viking ancestors with remarkable clarity, unmarred by centuries of genetic mixing that transformed other European populations. The first hints that something unusual existed in Faroes' genetics emerged not from cutting-edge research laboratories, but from the careful observations of rural physicians making house calls in the 1960s. Dr. Johannes Nielsen, a Danish physician stationed at the Tórshavn Hospital in the Northern Islands, began noticing patterns in his patient records that defied statistical probability. Over a 3-year period from 1962 to 1965, Dr. Nielsen documented 7 cases of severe progressive muscle weakness in children from 4 different families, all living within a 20-kilometer radius. The condition, which he initially couldn't identify, caused affected children to struggle with basic physical activities by age 10, with symptoms worsening through adolescence. Medical textbooks suggested such clustering was impossible for rare hereditary conditions. By the 80s, systematic medical record analysis began in earnest. Dr. Olavur Mortensen, appointed as chief physician for the Faroese health system, initiated the first comprehensive review of medical records dating back to the 1920s. What he discovered was both fascinating and troubling. Local doctors had long documented what they called family diseases, conditions that appeared repeatedly within specific family lines across multiple generations. The breakthrough came in 1987, when genetic testing technology became sophisticated enough to identify the specific mutations causing these conditions. Dr. Mortensen sent blood samples from affected families to laboratories in Copenhagen and discovered that the muscle weakness Dr. Nielsen had documented decades earlier was phosphofructokinase deficiency, a metabolic disorder so rare that fewer than 200 cases had been documented worldwide since its discovery in 1965. But the Faroe Islands, with a population of just 45,000 at the time, had documented 23 cases. The investigation rapidly expanded. Dr. Maria Petersen, a Faroese neurologist who had trained in Denmark, returned home in 1995 to establish the island's first genetics program. Working with Dr. Numi Gregersen from the University of Southern Denmark, she launched a systematic survey of hereditary conditions across the islands. Their initial findings were staggering. Phosphofructokinase deficiency occurred at a rate of approximately 1 in 1,000 births in the Faroe Islands, 100 times higher than the global average. But it wasn't alone. Hereditary amyloidosis, a progressive condition causing organ failure, appeared at 1 in 500 births, compared to 1 in 50,000 globally. Retinitis pigmentosa, an inherited form of blindness affecting young adults, occurred at 1 in 300 births, versus 1 in 4,000 worldwide. By 1998, researchers had documented elevated rates of at least 15 different genetic conditions, each following clear inheritance patterns through Faroese family lines. The medical community faced an unprecedented situation, an entire population carrying concentrated genetic variants at rates never before documented in modern Europe. The initial community response was complicated. Many Faroese families had long known about hereditary conditions. Grandmothers warned granddaughters about the family weakness, and informal marriage avoidance existed between families known to share certain conditions. But formal genetic research triggered concerns about stigmatization, discrimination, and privacy. Pastor Jakob Hansen, a respected community leader in Tórshavn, voiced concerns shared by many. Our ancestors survived here for 40 generations. Are we now saying they were genetically defective? Will this research be used to suggest Faroese people shouldn't have children? To understand how the Faroe Islands became a genetic time capsule, we must trace the population's history through 12 centuries of isolation, examining how geography, culture, and chance combined to create one of the world's most genetically unique populations. The story begins in 825 AD, when Norse Vikings first settled the uninhabited Faroe Islands. Population geneticists estimate the founding population comprised between 60 and 100 individuals, primarily from western Norway, with possible contributions from Norse settlements in Scotland and Ireland. This small founding group created what geneticists call a population bottleneck. a dramatic reduction in genetic diversity that would shape Faroese genetics for centuries. From 1000 to 1400 AD, medieval isolation intensified this genetic bottleneck. The conversion to Christianity in 1000 AD brought cultural changes that paradoxically increased isolation. The Catholic Church and later Lutheran authorities after the Reformation discouraged marriage outside the community. Historical records from the period show remarkably little immigration. Perhaps fewer than 200 individuals joined the population over 4 centuries. Church records, which begin in the early 1600s, provide extraordinary documentation of this isolation. The Danish Lutheran Church required meticulous baptismal, marriage and death records for every Faroese parish. These records, preserved in the National Archives in Copenhagen and the Faroes National Archives in Tórshavn, enabled modern geneticists to construct complete family trees spanning 15 to 20 generations for virtually the entire population. Dr. Numi Gregersson's team spent 5 years digitizing and analyzing these records, creating what became the Faroese genealogical database, a comprehensive record of family relationships for every Faroese individual born since 1600. The analysis revealed stunning patterns of consanguinity. By the 1800s, most Faroese individuals were at minimum 5th or 6th cousins to nearly everyone else on the islands. The genetic implications became clear when researchers combined genealogical data with modern DNA analysis. Between 1995 and 2005, Dr. Petersen's team collected DNA samples from over 15,000 Faroese individuals, nearly 1/3 of the population, creating one of the world's most comprehensive population genetic databases. The results confirmed what church records suggested. The entire modern Faroes population descended from an original founding group that was itself genetically limited. Computer modeling suggested that 90% of current Faroes' genetic variation could be traced to approximately 75 founding individuals. This meant that rare genetic variants, carried by just 1 or 2 of those original Norse settlers, became relatively common in their descendants. The mechanism driving this phenomenon is called genetic drift. Random changes in genetic variant frequencies across generations. In large populations, rare variants remain rare. But in small isolated populations, rare variants can become common simply by chance, especially if the individuals carrying them have many descendants. Phosphofructokinase deficiency provided a perfect example. Genetic analysis revealed that all affected Faroese individuals carried an identical mutation, suggesting a single ancestor brought this variant to the islands more than 1,000 years ago. In a large, genetically diverse population, this variant might have disappeared or remained extremely rare. But in the isolated Faroe Islands, the descendants of that original carrier intermarried over generations, eventually creating a population where approximately 5% of individuals carried the mutation. The autosomal recessive inheritance pattern meant that individuals with 1 copy of the mutation were healthy carriers, while those inheriting 2 copies, 1 from each parent, developed the disease. With such a high carrier rate, the probability of 2 carriers having children together became significant, resulting in the island's elevated disease rates. Dr. Anders Berglum, a population geneticist from Aarhus University who collaborated on the Faroes research, explained the implications in a 2008 interview. The Faroe Islands represent evolution in action, demonstrating how small population size and geographic isolation can dramatically alter genetic architecture within just 40 generations. What we're seeing is essentially a controlled natural experiment in human population genetics. The geographic isolation compounding this genetic isolation was severe. Village structure on the island's reinforced population subdivision. Most of the 18 islands are separated by treacherous ocean channels, and until the 1980s, regular inter-island travel was difficult and dangerous. Individual villages, typically comprising 50 to 500 people, were often isolated by terrain even on the same island. This created what geneticists call population substructure. Genetic differences between villages despite their geographic proximity. Some genetic conditions appeared primarily in northern island villages, while others concentrated in southern communities, reflecting the specific founding families of each settlement. Cultural factors reinforced geographic isolation. The Faroes' maritime economy, centered on fishing and traditional whale hunts, created tight-knit communities with strong clan loyalty. Marriage typically occurred within villages or between neighboring communities with established ties. While not formally prohibited, marriage to outsiders, even Danes or Norwegians, was uncommon until the mid-20th century. Traditional Faroese society had developed informal knowledge about hereditary conditions. Community elders in villages like Elduvik and Funningur spoke of family illnesses that appeared across generations. Some families were known to carry the seeing disease, retinitis pigmentosa, while others were associated with the muscle weakness, phosphofructokinase deficiency. This traditional knowledge sometimes influenced marriage decisions, but without understanding genetic mechanisms, these practices provided incomplete protection. The transformation from genetic discovery to medical intervention began in 1992, when the Danish government, responding to preliminary Faroes research findings, allocated 12 million Danish kroner for a comprehensive genetic research initiative. This marked the first time a European government had funded population-wide genetic research for a specific community. The Danish Ministry of Health appointed Dr. Olavur Mortensen as director of the newly established Faroese Genetic Research Program. His mandate was unprecedented: create a systematic approach to documenting, understanding, and ultimately reducing the burden of hereditary disease in the Faroe Islands, while respecting community autonomy and cultural sensitivity. The first challenge was legal and ethical. Denmark's existing genetic research regulations designed for individual patient care didn't adequately address population-wide genetic studies. Between 1992 and 1998, Danish and Faroese authorities worked together to develop new regulatory frameworks that would balance scientific research, medical care, and individual privacy. The result was the Faroes Genetic Protection Act of 1998, groundbreaking legislation that established several critical principles. First, participation in genetic research must be voluntary and informed, with clear explanations of how genetic information would be used. Second, genetic information belonged to individuals and families, not researchers or government authorities. Third, genetic data could not be used for employment discrimination, insurance decisions, or social stigmatization. With legal framework established, the Faroes Genetic Database was officially created in 1998, headquartered at the National Hospital of the Faroe Islands in Tórshavn. Dr. Maria Petersen was appointed Chief Medical Officer for Genetic Services, overseeing both research and clinical care. The database's creation immediately enabled more sophisticated analysis. By linking genealogical records, medical histories, and genetic samples, researchers could trace the inheritance of specific conditions through multiple generations with unprecedented precision. Between 1998 and 2005, the database grew to include genetic information from over 20,000 individuals, nearly half the population. Medical intervention began with comprehensive genetic counseling. In 2000, the Faroese health system established the first dedicated genetic counseling service in the North Atlantic region outside Reykjavik. Trained genetic counselors working closely with Dr. Petersen's team offered free consultations to any Faroese family planning to have children. The counseling process was straightforward but powerful. Couples received genetic screening to determine if either partner carried mutations for known Faroese conditions. If both partners were carriers for the same recessive condition, counselors explained the 25% risk that each child would inherit both copies and develop the disease. Families then made informed decisions about family planning, armed with scientific knowledge their ancestors lacked. The impact was measurable. A 2006 study published in the European Journal of Human Genetics documented that genetic screening and counseling had reduced births of children affected by phosphofructokinase deficiency by 60% over a 6-year period. Critically, this reduction came entirely through informed family planning decisions. There was no government mandate or social pressure, simply families choosing to use genetic information in their reproductive decisions. Prenatal screening capabilities, introduced in 2003, provided additional options. Pregnant women whose genetic profiles indicated risk could receive prenatal diagnosis through chorionic villus sampling or amniocentesis, allowing families to understand their child's genetic status before birth. This information helped families prepare for medical care needs, or in some cases, make difficult decisions about pregnancy continuation. The breakthrough that transformed Faroese genetic medicine came in 2001, when an international consortium led by Dr. Gregersen received European Union approval for the first gene therapy trial targeting a Faroese-specific genetic condition. The trial focused on carnitine transporter deficiency, a metabolic disorder affecting approximately 1 in 300 Faroese births, compared to 1 in 70,000 globally. Carnitine transporter deficiency prevents cells from properly utilizing fatty acids for energy, leading to severe cardiac problems, muscle weakness, and potentially fatal metabolic crises during illness or fasting. Traditional treatment required lifelong carnitine supplementation, effective but requiring strict adherence and regular monitoring. The gene therapy trial, conducted between 2001 and 2005, involved 12 Faroese patients with carnitine transporter deficiency. Using modified adenovirus vectors, researchers attempted to deliver functional copies of the SLC22A5 gene, which produces the carnitine transporter protein, to patients' cells. Initial results were promising. 9 of 12 patients showed improved carnitine transport and reduced symptoms over the 2-year trial period. Building on this success, in 2012, the Faroese health system, in partnership with Copenhagen University Hospital, launched stem cell therapy trials for several metabolic disorders. The approach involved harvesting patients' own stem cells, using CRISPR gene editing to correct disease-causing mutations, and transplanting the corrected cells back into patients. By 2018, these experimental therapies had progressed sufficiently that the Danish Medicines Agency approved expanded CRISPR gene editing research, specifically for Faroese genetic conditions. The approval recognized that the island's unique genetic situation, with clearly defined mutations affecting substantial patient populations, made them ideal for developing and testing genetic therapies that could eventually benefit patients. Worldwide, international collaboration accelerated during this period. The Faroese genetic database became a resource for researchers globally studying rare genetic conditions. Between 2005 and 2020, over 40 international research institutions partnered with Faroese scientists, contributing both expertise and funding to genetic research that provided benefits far beyond the islands. Major pharmaceutical companies also recognized the opportunity. The clearly defined genetic causes of Faroese conditions, combined with comprehensive medical records and patient willingness to participate in research, made the islands attractive for clinical trials. Companies like Novartis, Roche, and Sarepta Therapeutics established research collaborations focused on developing therapies for metabolic disorders, neuromuscular diseases, and hereditary organ conditions. This international attention brought both benefits and concerns. On one hand, Faroese patients gained access to cutting-edge experimental treatments unavailable elsewhere. On the other hand, community members worried about becoming genetic guinea pigs for international corporate interests. The Faroese government responded by strengthening oversight, ensuring that any commercial research provided direct benefits to Faroese patients, and that the community maintained control over how genetic information was used. By 2010, the Faroe Islands had transformed from a population unknowingly carrying concentrated genetic disease into a community at the forefront of genetic medicine. This transformation required not just scientific advances, but fundamental changes in healthcare infrastructure, education, and community understanding of genetics and heredity. The centerpiece of this transformation was the establishment of the Faroese Genetic Medicine Center at the National Hospital in Tórshavn in 2008. This specialized facility, funded jointly by the Faroese government and the European Union, provided comprehensive care for patients with hereditary conditions. The center housed genetic counseling services, specialized diagnostic equipment, and treatment facilities specifically designed for managing genetic metabolic disorders. Medical treatment capabilities expanded dramatically during this period. For patients with phosphofructokinase deficiency, the center established comprehensive management protocols that combined dietary modification, physical therapy, and experimental enzyme replacement therapy. While curative treatment remained elusive, proper management significantly improved quality of life and reduced hospitalizations by 70% compared to historical outcomes. For hereditary amyloidosis patients, advances were even more dramatic. The condition, caused by abnormal protein deposits in organs, had historically been invariably fatal within 15 years of diagnosis. But in 2011, collaboration between Faroese physicians and researchers at the Mayo Clinic led to successful liver transplantation combined with stem cell therapy for 3 Faroese patients. This approach, which addressed the liver's role in producing abnormal proteins while regenerating affected organs, provided the first hope of long-term survival for affected individuals. Treatment for retinitis pigmentosa, the inherited blindness affecting Faroese families, progressed through multiple stages. Initial efforts focused on vitamin A supplementation and protective eyewear to slow disease progression. By 2015, gene therapy trials using subretinal injection of adeno-associated virus vectors carrying functional copies of affected genes showed promise in halting vision loss in early-stage patients. 3 Faroese teenagers participated in these trials, with 2 showing stabilized or slightly improved vision over 3 years of follow-up. Beyond individual treatments, community-wide adaptation to genetic knowledge transformed Faroese society. The education system integrated genetics into school curriculum, with age-appropriate lessons beginning in primary school. By 2012, every Faroese student received education about heredity, genetic conditions, and family planning by the time they reached secondary school. This educational focus reflected a broader cultural shift. Rather than viewing genetic conditions as shameful family secrets, Faroese society increasingly embraced openness about hereditary disease. Support networks emerged for families affected by specific conditions. The Faroese phosphofructokinase Support Association, founded in 2005, brought together affected families for information sharing, emotional support, and advocacy for research funding. Community elder Suni Karlsberg, whose family had been affected by hereditary conditions for generations, described the transformation in a 2021 interview. "When I was young, we didn't speak about these illnesses outside the family. There was shame, as if we had done something wrong. Now my grandchildren learn in school about the genes they carry. There's no shame, just knowledge and preparation." Marriage patterns and family planning evolved with genetic knowledge. Premarital genetic counseling became culturally normalized, though never required. By 2015, surveys indicated that approximately 60% of Faroese couples planning marriage sought genetic counseling voluntarily. This wasn't about preventing marriages between carriers. Rather, couples wanted to understand their genetic risks and plan accordingly. The healthcare infrastructure supporting this work expanded significantly. Between 2008 and 2020, the Faroese health system trained 12 genetic counselors, hired 6 specialists in metabolic medicine, and established specialized pediatric care for children with genetic conditions. This represented a massive investment for a population of 50,000, but the results justified the cost. Hospital admissions for genetic metabolic crises decreased by 65%, and the overall health outcomes for affected individuals improved dramatically. Research outcomes from Faroese genetic studies produced broader medical benefits. Between 2000 and 2020, studies using Faroese genetic data contributed to the identification of 23 new disease genes, genetic variants whose roles in human disease weren't previously understood. These discoveries had implications far beyond the Faroe Islands, advancing understanding of rare diseases affecting patients worldwide. The research also led to practical treatment developments. 8 new therapeutic approaches for rare metabolic and neuromuscular disorders entered clinical trials based partly on insights from Faroese genetics. Drug discovery efforts specifically targeted pathways identified through studying how Faroese genetic variants affected cellular function. Improved diagnostic tools represented another major impact. The clear genetic signatures in Faroese conditions allowed researchers to develop more sensitive screening methods. Newborn screening protocols developed for Faroese conditions were subsequently adopted by other Nordic countries and beyond, enabling earlier diagnosis and treatment for affected children worldwide. Medical literature reflected this impact. Over 200 peer-reviewed publications between 1995 and 2020 reported research based on Faroese genetic studies. The Faroe Islands, with 0.07% of the world's population, contributed disproportionately to human genetic knowledge, punching far above their weight in advancing medical science. The broader medical impact extended to population genetics theory. The Faroes provided the clearest real-world example of genetic drift and founder effects documented in any modern human population. Textbooks in genetics and evolutionary biology routinely cited Faroese studies when explaining how isolation affects genetic diversity. Cultural preservation remained a priority throughout this scientific transformation. The Faroese Genetic Heritage Project, initiated in 2016, explicitly framed genetic knowledge as part of cultural identity rather than opposed to it. The project created educational materials, museum exhibitions, and digital resources explaining how the island's unique history created their unique genetic legacy. This framing proved crucial for maintaining community support. Rather than viewing genetic research as threatening Faroese identity, most community members came to see it as honoring their ancestors while protecting future generations. The Viking settlers who arrived in 825 AD couldn't have imagined that their decision to settle remote islands would create a genetic legacy lasting 1,200 years. But their descendants chose to face that legacy with courage and scientific rigor. As we approach 2025, the Faroe Islands' genetic journey stands as one of the most remarkable stories in modern medicine, demonstrating how geographic isolation created both unique challenges and unprecedented opportunities for advancing human health. The long-term impacts extend far beyond the islands themselves. Between 2014 and 2024, Faroe's genetic research directly contributed to breakthrough discoveries that benefited patients worldwide. A 2022 study published in Nature Genetics, using data from the Faroes genetic database, identified previously unknown genetic modifiers that influence disease severity in metabolic disorders. These findings enabled more precise prognosis and personalized treatment approaches for thousands of patients globally with similar conditions. The Faroes research model, combining comprehensive genetic data, detailed genealogical records, and complete medical histories, became a template for other isolated populations. Iceland, Sardinia, Finland, and French Canada all established similar population genetic research programs, inspired by Faroes' successes and learning from their challenges. Global medicine integrated lessons from Faroes genetics into clinical practice. The understanding that genetic drift could concentrate rare variants in isolated populations led to enhanced screening recommendations for other founder populations. Medical schools incorporated Faroes case studies into genetics curricula, teaching future physicians about population bottlenecks, consanguinity, and the interplay between geography and genetics. The research established new standards for ethical genetic research. The Faroes Genetic Protection Act became a model for balancing scientific investigation with individual rights and community autonomy. International bioethics discussions frequently referenced Faroes' approaches when debating how to conduct genetic research with isolated or indigenous populations. Policy changes extended beyond the islands. The Nordic countries, observing Faroes' successes, established the Nordic Genetic Medicine Collaboration in 2018, creating a framework for sharing genetic data, coordinating research, and developing joint treatment protocols for rare hereditary conditions across Denmark, Iceland, Norway, Sweden, and Finland. Faroese educational reforms influenced broader genetic literacy efforts. The systematic approach to teaching genetics in Faroes schools, which successfully raised community genetic knowledge without increasing anxiety or stigma, was adapted by educational systems in multiple countries seeking to improve public understanding of genetics. Medical tourism emerged as an unexpected development. By 2020, patients from around the world with rare metabolic disorders were seeking evaluation and treatment at the Faroes Genetic Medicine Center, attracted by the institution's specialized expertise. This reversed the traditional pattern where Faroes patients traveled to Copenhagen or other major cities for specialized care. New regulations ensured that medical tourism supported rather than burdened the local healthcare system, with visiting patients subsidizing care for Faroe's residents. Dr. Maria Petersen, reflecting on 25 years of genetic medicine work in a 2020 interview, offered perspective on what the island's experience revealed. Working with Faroe's genetics taught us that isolation is a double-edged sword. Our Viking ancestors' isolation preserved not just our culture, but also their genetic legacy, both the good and the harmful. What we've learned from studying our own genetics has led to treatments that help patients around the world. The Faroes proved that genetic isolation isn't just a local problem. It's a window into human biology that benefits everyone. Her words captured the transformation in how Faroese society understood its genetic heritage. What began as a potentially stigmatizing revelation that centuries of isolation had created concentrated genetic disease evolved into a source of pride. The Faroes hadn't just survived their genetic challenges, they had turned them into contributions to global medical knowledge. Community perspectives evolved in parallel with scientific understanding. Suni Karlsberg, the community elder whose family had been affected by genetic conditions, offered his reflection in 2021. Our ancestors never intended to create genetic problems when they settled these islands. But when modern medicine showed us what isolation had done to our genes, we had to act. Understanding our genetics didn't make us less Faroes. It made us better guardians of our children's health. We can preserve our Viking heritage while protecting our genetic future. His perspective reflected broader community sentiment. Surveys conducted in 2019 showed that 82% of Faroese adults viewed genetic research positively, believing it enhanced rather than threatened cultural identity. This represented a dramatic shift from the skepticism and concern that greeted early research initiatives in the 1990s. The medical infrastructure supporting genetic health became permanently integrated into Faroese healthcare. The Faroes Genetic Institute, established as an independent research institution in 2017, ensured continuity of genetic research and clinical care. With a staff of 45 and an annual budget of $8 million, funded by a combination of Faroese government, Danish contributions, and international research grants, the institute represented one of the world's premier facilities for population genetic research. International databases incorporated Faroes' genetic information, with appropriate privacy protections, into global resources for genetic research. The International Database of Human Genetic Variation, the Global Alliance for Genomics and Health, and multiple disease-specific genetic databases all included Faroes data, enabling researchers worldwide to study rare genetic variants and their effects. Medical training programs established fellowship opportunities in population genetics at the Faroes Genetic Institute. Between 2017 and 2024, over 60 physicians and genetic researchers from 25 countries completed fellowships in the Faroe Islands, learning both technical skills and ethical approaches to working with isolated populations. These fellows carried Faroes lessons back to their home institutions, spreading best practices globally. Research contributions continued expanding. By 2024, Faroes' genetic studies had contributed to improved understanding of neurological diseases, including rare forms of epilepsy and movement disorders. Metabolic medicine advances based partly on Faroes' research led to new treatments for enzyme deficiencies affecting patients worldwide. Ophthalmology research using Faroes patients with retinitis pigmentosa contributed to gene therapy approaches now in clinical trials internationally. Cultural preservation efforts deliberately integrated genetic heritage into broader Faroes identity. The National Museum of the Faroe Islands opened a permanent exhibition in 2023 titled From Vikings to Genes, the Faroes Story, which explained how the island's history created their unique genetic legacy. Rather than presenting genetics as a medical problem, the exhibition framed it as part of the remarkable story of human adaptation and resilience. The exhibition proved enormously popular, becoming the museum's most visited display and attracting tourists interested in the island's unique scientific story, alongside their dramatic landscapes and preserved Viking culture. This demonstrated that genetic heritage could become a positive element of cultural identity when properly understood and contextualized. Looking forward, the Faroes' genetic legacy continues evolving. The latest genetic technologies, including next-generation sequencing and advanced gene editing approaches, promise further improvements in diagnosis and treatment. Research initiatives launched in 2024 are exploring whether targeted gene therapy could effectively cure some hereditary conditions by correcting mutations in affected individuals. The broader implications of the Faroes' experience extend to fundamental questions about human diversity, adaptation, and resilience. The islands demonstrated that geographic isolation doesn't just preserve culture, it preserves genes, both beneficial and harmful. This has implications for understanding human evolution, explaining disease distribution in diverse populations, and appreciating how history shapes biology. Population geneticists studying human history increasingly recognize that most human populations have experienced periods of isolation and genetic bottlenecks, similar to, though usually less extreme than, the Faroes' example. Understanding these historical bottlenecks helps explain why certain genetic diseases cluster in specific populations, why genetic ancestry matters for medical care, and how human genetic diversity arose from our species' complex history of migration, isolation, and mixing. The Faroe Islands thus serve as a model, both cautionary and inspiring, of how human populations adapt to challenging circumstances, and how modern science can address inherited challenges while preserving cultural identity and community autonomy. Before we close, let us know in the comments, does your family have any hereditary conditions or unique genetic traits? How has understanding genetics influenced your family planning or health decisions? We'd love to hear your experiences from wherever you're watching around the world. The Faroe Islands' genetic journey transformed isolation into collaboration, genetic burden into medical breakthrough, and potential stigma into scientific contribution. Their 200-year experiment in island living accidentally created one of medicine's most valuable research populations. Today, as we advance genetic technologies and precision medicine, we must remember the lesson of the Faroes. Genetic isolation can preserve culture and create challenges, but genetic knowledge preserves lives. Because the Faroes proved that understanding our genetic heritage doesn't diminish our cultural identity. It empowers us to protect future generations while honoring our ancestors' legacy. The Vikings, who settled those remote islands in 825 AD, brought more than their culture across the North Atlantic. They brought their genes, and 12 centuries later, their descendants turned that genetic inheritance into gifts for the entire world, advancing our understanding of human biology, pioneering new treatments for rare diseases, and demonstrating that even the most isolated communities can make global contributions to human knowledge and well-being. The story of the Faroe Islands reminds us that we are all products of our history, both cultural and genetic. How we choose to understand and respond to that inheritance determines not just individual futures, but our collective capacity to overcome inherited challenges and build healthier futures for generations to come.